Toss the coin infinitely many times. Infinitely many times. Okay, so in this case, what will be the sample space? Anybody? Anyone?
So a sequence of heads and tails, sir. The one
So
point will be a sequence of heads and tails. Like suppose head, tail, head. My, it will
okay,
be an infinite set collection, infinite sets of infinite collection.
right.
Like the
So if you
sequence of
look,
set of sequences, sir.
yeah. So if you look at each sample point, as Sumit mentioned, it will be a sequence of heads and tails, right? So one way to write that is, I'll write it as, denote it as omega 1, omega 2, and so on. Okay, it's an infinite sequence such that if you look at any of these omega I, it will be either head or tail, right? And I is 1, 2, 3, etc. This will be your sequence. So the collection of such infinitely many sequence will constitute our sample space. Is that fine, everyone? So now, so each one of this infinite sequence is an outcome or a sample point. So now I can ask, what is the probability of one such sequence? Let's say omega 1, omega 2, etc. What do you think is the probability? Intuitively. So I haven't started probability theory formally, but informally or based on your undergrad knowledge, you could perhaps easily answer this, right? So what will be the probability?
One
Huh?
probability of entire sample space, right?
Not the entire sample space, the probability of this particular sequence. Okay. Maybe you can think for concreteness, you can think of probability of head, tail, head, tail, head, tail, head, tail, and so on. What is the probability of that particular sequence to occur when you toss a fair coin infinitely many times?
So it should tends to zero, I think, sir.
Zero, zero, zero.
Right? Yeah. So what will happen? So you are absolutely right. So the probability of head or a tail is half half. So you are looking at infinite sequence. So it will be essentially 1 by 2 power n for n tosses. So it should be 0, right? That's what you get, right? Why? Why is it? So there is an issue with this, right? For example, if you look at, let's look at another example. So I'll continue. I'll come back to this example a little later. So let's look at another example. Let's say you throw a dice. Okay. So what will be the sample space? Very easy. 1, 2, 3, 4, 5, 6. Let's assume it's a fair dice, meaning the probability of 1 or 2 or 3, any of them to occur will be 1 by 6. Now, let's look at the following three events, whatever the events mean. So, the first event is 1, 2, 3. The second event B is 4, 5. The third event is 6. Okay. So, now these are all disjoint, right? Because if 3 occurs, 4 or 5 cannot occur, so they are disjoint. Now you look at the union of these events. So let me call this as A1, not sorry, A union B union C will be omega. You agree? So if you glue all the pieces, you get the entire set. So the probability of one of these things to occur, right? So A union B union C, which is nothing but the probability of the entire set omega. You are asking what is the probability of one of the 6 possible outcomes occur, which is 1 obviously, but this is also equal to probability of A plus probability of B plus probability of C, right? For example, probability of A is 1 by 2, probability of B is 2 by 6, which is 1 by 3, and probability of C is 1 by 6. If you add them, you get 1, right? So in other words, the probability of union of pieces, disjoint pieces, will be equal to the sum of the probabilities of each piece. Right? Whereas if you go back to the previous example, this is a particular sequence, right? This is one particular sequence. Now you are saying this particular sequence the probability of that is 0, no matter which sequence you pick. Now, if you look at omega, it's like basically many such sequences, right? When you take the probability of union of all those pieces, we should get 1, but whereas you are getting 0 plus 0 plus and so on, by the end of the day, you'll get 0. So, can anybody recognize what is the issue here? You understood the issue? Understood the issue here? So if you look at 1, 2, 3, 4, 5, 6, you look at probability of union of disjoint piece, that will be equal to sum of the probabilities. Whereas here, disjoint outcomes, if you take the probability of the union, it will be not equal to the sum of the probabilities, because some of the probabilities will be 0 plus 0 plus 0 and 0, but probability of union will be omega, which is 1, right? One of them should occur. So what is the issue?
Sir, maybe the 0 that we are getting is not the exact 0, it is tending to 0. So,
no, of course, it's not tending to 0. That's not correct. It's exactly equal to 0. That means if you practically conduct this experiment, you will never observe such a sequence. Nitish, you want to say something?
Yeah, sir, because as the coin is fair, no, sir, in the last example, sir, coin was a fair. So in a long run, we are not going to get like sequence head, tail, means ultimately we just come up the in a
No,
situation
it
where,
has got nothing to do with fair or unfair, right? As long as the probability is less than 1.
okay,
Now you are, suppose some fraction of, so you will be taking something that is less than 1 to the power of something that goes to infinity, right? So obviously you will get 0.
yeah, sir.
Unless the probability of head is 1, then you only have one sequence that occurs, head, 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 head.
So is there anything to do with countable and
Very good,
uncountable
right? Very
set?
good. So can somebody comment more on that? Countable versus uncountable. Sumit, maybe you are from math background. Okay, Rishabh, can you elaborate more on that?
So the dice
Yeah,
from
sir.
experiment is a countable number of steps. So
Yeah,
What
sir, I
about this
think,
guy? What about, for example, these sequences, omega 1, omega 2, etc. So if you look at each outcome and looks like it is countable, right? What can you say about that?
also uncountable, there is finite countable and infinitely uncountable. Is there anything?
No, so the moment if it is finite, obviously it has to be countable. There is no question there. The moment you say infinite, then the question of whether it's countable or uncountable will come, right? Right. So it turns out, okay, I'll answer this. Maybe as and when we move further, most of you should think about this and answer. So
is this anything to do with central limit theorem?
Not well. What exactly are you saying?
Sir, I really don't.
Well, this example as such, not really. I mean, well, we will look at central limit theorem in this context also, but let's not worry about that. Let's only look at this particular thing now, and let's see central limit theorem when we deal with that. Okay. So essentially, it turns out that this sequence, right, this collection of omega 1, omega 2, etc. So if you look at this, if you collect all such sequences, it's not really a countable set of sample points. It's uncountable. Okay. These things form uncountable set of sample points. Therefore, if you ask what is the probability of each point, it will be 0. So let me give you another example. Okay. This is the third example that we will look at. Suppose I have a disk and I rotate the disk and measure the angle. So angle could be anywhere between 0 to 2 pi. So omega will be 0 to 2 pi closed. Now, if you ask what is the probability of, let's say, angle that you observe is pi by 2, what is the answer? Any idea? So in other words, I have a disk, I rotate the disk. Okay, this is the point. I rotate the disk, and I am going to measure the angle with respect to this particular line. So for example, if the disk ends up here, then the angle is theta. Okay, theta is random between 0 to 2 pi. So what is the probability of angle being pi by 2? What do you think is the answer practically?
0, sir.
0, right? How many of you think that it's 0?
Yes, sir. 0, sir.
0, right? So that's because when you rotate the disk, there are uncountably many choices, right? 0 to 2 pi has uncountably many numbers. So the probability of each point to occur is 0. So if you ask this question, the answer will be 0, but you cannot say that it is a so when you want to make this 0 to 2 pi set, you cannot take countably many pieces, take the union and get 0 to 2 pi. You have to take uncountable union, right? So if you look at discrete case, you will be looking at probability of union of countable sets, which makes the entire piece. And you say that, well, that probability is 1, but whereas here it will be uncountable. Okay, so even in the previous example, throwing a this infinitely many tosses, each point is like, it constitutes, when you take the uncountable union, you get the entire omega, but it appears as if it is like countable. But those who are inclined towards mathematics, I would encourage you to show that this set is uncountable. Okay, how many of you are interested in math, by the way? Of course you should be, that's why you did your master's.
Yes, sir. We can prove it, sir. Like we can show bijection from the binary representation of the real number lying between 0 and 1 to this set, sir.
Okay, so you can try that. Rishabh, you had a point, right? So you wanted to say something?
No, sir, I'm also interested. That's right.
Okay, so I think those who are interested, you can discuss and try to come up with a proof for this. As he correctly mentioned, I can map head to 1 and tail to 0. And suppose I get a sequence 1 0 1 1 0 0 and so on. I put a point just before that, 0.11 something, binary representation of decimal. And I can show that every point on 0 1 can be, there is a bijection between any point on the real line 0 1 to this particular representation. That's what Sumit is saying. Okay, so Himanshu, you have any question?
No, sir.
No. Okay, so please engage in the discussion. Okay, so if you don't understand, just ask me. Don't keep accumulating all the confusions, doubts. It can only keep increasing, and finally you won't be able to understand anything. Okay, anyway, so there is this issue of countability here. Okay, so now the question is, what is the problem in probability? So what is the big problem? Well, problem in the sense, not so what is the question that we will ask? Okay, so just to give you a big picture, so we have two things. One, you have experiment, and you have the set of all outcomes called sample points, and then you have to associate a number called chances or probability to certain subsets of this. Okay, so ideally I want to have a subset which is this universal set, right? So set of all outcomes, and I want to assign a probability to it. Okay, so this is what I want. When I assign probability, I cannot assign it in a random fashion. It has to sort of follow certain rules. Where do you get these rules from? Based on the problem, right? So in probability, you have certain rules that you need to follow. Or if you take tossing a coin, you have certain things, right? So probability of head to occur is some number between 0 1. Probability of tail to occur will be 1 minus probability of head. Probability of head or tail to occur is 1, and so on. So you have certain set of rules that you need to adhere to, and you should assign a number called probability to every subset. That is our big wish, right? So this will be our big wish. Okay, now it turns out that for example, let's take an example even here. So head tail, so omega is head tail. Then what is 2 power omega? It's head, tail, head, tail, and of course null set. Okay, this is your 2 power omega. So what is the probability here? How do you assign probability? So probability of head to occur is, let's say, p. Probability of tail to occur would be 1 minus p, and probability of omega is 1. So I'll just write that probability of omega is 1. Probability of null set is 0, right? So this describes the scenario completely, because I have the sample space, I have set of all subsets. Each of these things are called events. Okay, so let me use, these are called events. So I can assign probability, I have assigned probabilities to each of these events. So that sort of completes the story. Okay. Now the question is, well, for head tail I can do, for 1, 2, 3, 4, 5, 6, which is dice, I can do a similar thing. In fact, for any countable outcomes, I can do something similar. But the question is, can I do something similar for this guy, this particular example, omega equal to 0 to 2 pi? Can I take every subset and try to assign a probability, a number called probability? That's the question. Okay. It turns out, okay, so I'll write this in bold. Turns out that one cannot assign probability, well, in a reasonable fashion. So you can assign some random numbers, obviously, but reasonable fashion, whatever reasonable means. Okay, you cannot assign probability to every subset of the sample space omega for all experiments, right? Of course, for the above experiment wherein you had countable outcomes, we could do this, but it's not true for all. So why? It has got something to do with measure theory. So if you take a course in measure theory, they will teach you or they will construct a weird subset. Basically, that's what they will show. They will take this is omega. They will basically cut this into weird two sets, let's say A and B. A and B disjoint. You expect probability of A union B to be equal to probability of A plus probability of B. Okay, just to keep it general, I'll also add as this is your omega. Okay, so I'm going to take a part of omega, which is A and B disjoint, but it's possible to construct two subsets A and B such that probability of A union B is not equal to this. That means no matter how you assign probability, I can take two pieces such that probability of A union B is not equal to probability of A plus probability of B when A and B are disjoint, which is against our intuition, right? Therefore, it is not possible. So now you need, so one approach is, you take a course in probability theory and figure out what are the subsets, if not the entire power set, what are the subsets that I can assign probabilities in a reasonable fashion. That's the question that you can ask, right? So that leads to two things. What do you mean by assigning probability? What are the rules of assigning probabilities? And the second thing is, what are the sets that I should consider for which I can assign probabilities? Okay, so that leads to an approach called axioms of probability. So axioms of probability theory. Basically, we are saying, well, Sumit will take measure theory course and he will come back and teach us what are the details there. But for now, we just take axioms of probability. Particularly, we will look at what is known as axioms of events. Okay.
Sir,
Yes.
the head-tail scenario, you mentioned the events HT, and for null. So H means that's the events containing only heads, and T means the events containing only tails.
No, don't think of it like that. So you think of this as questions, right? So what are the possible questions? Suppose I throw a dice, right? 1, 2, 3, 4, 5, 6. This is omega. What are the possible questions that you can ask as far as probability is concerned? You can ask questions like, what is the probability of even numbers to occur, right? What does that mean? It's the probability of 2 or 4 or 6 to occur, right? Similarly, you can say what is the probability of odd numbers to occur. You can say what is the probability that multiple of 3 will occur, and so on, right? These are the events.
So there are also more events, like you mentioned only 4, right?
Yeah, there are many events.
Okay,
For
okay.
example, you can ask what is the probability that 1 or 2 occurs. For some reason, I'm
Okay.
interested in that, right?
Okay. Now I understand. Now I understand.
Yeah, ideally, you should be able to answer for every subset. Okay. But
Yeah, sir.
what
So,
I'm saying here is, one second, I'm saying here is
yeah,
that
sir.
it's not possible to answer that for every case. Yes, I don't know who, somebody was asking questions, right?
Yeah, sir. Actually, so the event, whatever the event, that must
Yeah.
be the subset of that sample points, the sample space,
Exactly.
sir. So
Absolutely.
it
Yeah.
could not exceed the 2 to the power omega. That is, whatever the event we
True,
take
true.
must contain to
It
that,
should.
no, sir.
Ideally, we want 2 power omega, but it turns out that we can't. Right?
Yeah,
We
sir. Or
cannot.
one more thing, sir. Suppose like in tossing a coin or in
Uh,
throwing a die, sir. So in every time the sample points will not be the like head and tail and 1, 2, 3, 4, 5. Like one may be interested in something another. Like in tossing a coin, maybe I am not interested in getting a head or tail. Maybe number of flips or number of means like I am just changing something my perception of viewing.
Correct. So
So
in that case, what you can do is you can say that,
yes,
well, my experiment is slightly different, although the fundamental experiment is tossing a coin. But
yeah,
for example, let's say I can give you another example. Suppose I toss the coin 5 times, right?
yeah, sir.
So it's fundamentally it's the repetition of the same coin toss 5 times, but you are interested in how what is the probability that I observe 3 heads in 5 tosses, right? That's a
Yeah.
different question that you are asking, but built from the fundamental experiment of tossing a coin.
Uh, yes, sir.
Okay,
Yeah, sir.
but the fundamental aspect here is the sample space omega.
Yes, sir. Okay.
Okay,
Hmm.
yeah. So let's look at axioms of events. So what are the properties of events of interest? Okay, so first, uh, what I'm going to do is I'm going to collect some set of subsets of omega and call those events. Okay, so maybe I'll formally define it. So let's say definition: a collection of subsets of omega denoted F for, how do I put this? So are called events if, first of all, the entire set should belong to F, right? I mean, if you are missing the entire piece in your set of in your subset of omega, then it doesn't make sense. What is the next thing? So for every A1, A2, etc. belonging to F implies union is also there. Okay. What is the other thing that you need? For every A in F, a complement also belongs to F. So what are these? Typically, I want to ask questions like, what is the probability of something to occur? Obviously, 1, right? That is required. So, for example, I may be interested in asking, what is the probability of this or that or something else to occur, right? Therefore, you need the unions. And sometimes, you have an event A. I would like to ask questions like, what is the probability of that event not happening, which is A complement, right? So intuitively, this is what we need. right? There is a name for this. This set F is called, well, I'll write it as a small note. This set F is called, can somebody answer? Maybe Ayush, you should be able to answer.
Yeah, sir. It's sigma
No, no,
algebra, I
no.
think.
Okay, I was asking Ayush. Ayush, if you know, if you haven't heard what Sumit said, maybe you can say.
Uh, sir, I don't
Hey, it's
remember it.
okay to say that I don't know. Okay, but Praveen, I think Prashant Wali taught you, right?
Sir?
Who taught you probability?
No, sir, it was not there in the
Oh, it was
course.
not there. Okay.
Okay.
Rishabh, do you know what it's called?
The universal set.
No, sir.
It's not universal set, obviously. Need not be universal set. Okay. Okay, so it's called Sigma algebra. Okay, Sigma algebra.
So it's
So
like it's kind of thing is also in matrices, like a span or whatever it's called. Like
which
if
one?
it, something like this also in the definition in vector algebra. I think if two vectors are there, their summation is also must be in that set.
There is a significant difference. So, in linear algebra, if you look at vector space, there are certain properties that need to be satisfied, right? It should be closed under addition. It should be closed under scalar multiplication. All that, right? So, a collection of that will make a space a vector space. So here, collection of subsets which satisfy certain properties, the entire set should be there. Countable union of sets should be there, and complement should be closed under complement, and it should be closed under countable union. Looks very similar, but conceptually they are different. Okay. So now, whenever I talk about, let's say by mistake, also if I say not mistake by suppose I mention about Sigma algebra, you know what it means, right? It's essentially set of all events of interest. That's how intuitively, that's what you should think. Fine. So you have this collection. So let me look at one example. In fact, I will look at a very stupid example. You have a sample space omega, and I'll just add a null set to it. Is this a Sigma algebra? Can you say? Obviously, it's a subset of omega, right? Omega phi is a subset of omega. So this is some subsets of omega. See, first of all, the entire set belongs to it because omega is here. Now we say sequence of sets in F union should be there. Obviously, you have only two sets here, omega and phi. Union is omega, so omega is already there. You take any set A, complement should be there. If you take omega, the complement is phi. Null set is there. If you take null set as A, the complement is omega, omega is there. So this is a trivial Sigma algebra. Okay. But nobody cares about this, right? So what is the use of having such a Sigma algebra? The answer is already known for all possible random experiments, right? For example, probability of omega is 1, probability of null set is 0. Enough, right? So we are not really interested in such trivial Sigma algebra. We want to ideally have every subset. By the way, this is also true, okay? So 2 power omega is a Sigma algebra. In fact, this is the biggest Sigma algebra, right? You cannot have anything more than this. So this has everything, right? All possible intersection, everything it has. So this is a rich collection of subsets. So this is also a Sigma algebra. So what we expect is somewhere in between. Okay, so you should have as many sets as possible, but at the same time, you should be able to assign probabilities to those events in such a way that certain rules of probabilities are met. Okay, so let's look at some of the consequences. So I will write this as maybe a lemma. So can somebody tell me what are the possible things? So the first thing is null set belongs to F. Why is that? Can somebody prove that?
Due to
null set
third
belongs
property, sir. Due to the third property, sir.
Yeah, complement, right? Omega belongs
Yes.
to F, so omega complement belongs to omega complement, which is null set. What else can you infer? For all A1, A2, etc. belonging to F, intersection over all I equal to 1 to infinity AI belongs to F. So it's closed under countable intersection. So what is the proof? I want somebody else to answer. So wait, maybe I'll start with Jayant. Jayant, are you there?
Yes, sir.
Can you answer? So if A1, A2, etc. are in F, I want you to prove it's closed under countable intersection. Intersection AI is there in F. So how do you prove that?
From second property,
Okay, from second property what?
sir, even if A1, A2 are disjoint or some, even if
No,
they're
it's for any A1, A2. It could even be equal, right? You
as
think, I mean, as master student, it's not like undergrad, okay? Even the exams won't be like, I'll ask the same theorem in the whatever I prove in the exam. No, you will be asked to use that theorem and prove something else. Okay, that's how the exams will be. So you should be able to think and then, make some logical arguments towards some final goal. Okay. Okay, Nitish, are you there? Nitish,
Yeah.
can you tell me?
Hello.
Yeah.
No, sir. I don't.
Okay. Himanshu,
Yes, sir.
can you tell me what is the proof?
Sir, we'll take all A1 into A1 intersection up to the infinity, because A1 to whatever is there, A1, A2 up to so infinity is the set of F. So means this property number B.
Yeah, you get union. So
Yes, sir. Not getting.
okay. So Ayush,
Sir, so can I take, if we take two sets, for example, A1 and A2, and sir, we can use that probability of A1 union.
there is no
A2.
probability here. So I haven't even introduced probability. Okay. So
Okay, sir.
probability
Using
is
the
out
set,
of the picture.
like that union of set A and set B is set A plus set B minus intersection of set A1 and set
No.
A2.
So what do you mean by that? So how can you subtract two sets? Sets could be donkey, monkey, whatever, right? So how do you subtract the two things? Jayant, you want to say something?
sir, as a null set also belongs to F. Yeah, even if the intersection of all A1 to AN, even if there is no common event, even that belongs to F, no sir.
Why? See, you have given three axioms. You are allowed to use only those three axioms. That's all. You cannot use your intuition and all that, right? So that's how you should proceed. It's almost like I don't know how to put it. It's almost like a lawyer arguing in the court, right? He cannot use his own whatever judgment to argue, right? He should use the laws, something like that.
Yes.
Yeah. Okay, Rishabh, can you?
Sir, can we prove it by somehow by induction? Like first we consider A1 and A2, Then we
well, you don't need induction here. Okay, fine. Let's assume that there are finite limits. A1, A2, etc. An belongs to F. Intersection I equal to 1 to N, Ai belongs to F. That's what you have to prove. What about others? They dropped out. Chandramani was there, right? So a few others were there in the last class, isn't it? Okay, Sumit, can you?
Yes, sir. Sir, as A1, A2, A3 all belongs to the F. So by the property third, sir, its complement will also be there.
Okay,
And
let me write
then,
that. Since
yeah,
A1, A2,
all these are in
etc.
F.
belongs to F implies
By
A1
property
complement,
3,
A2 complement,
yeah,
etc. belongs to F from C. Okay, I won't write that. From C,
okay, sir.
this follows. Okay,
Yeah.
what else?
And again from B, their union must belongs to the F.
So B union over all I equal to 1 to
Yeah.
infinity. AI complement belongs to F. Okay, then
Yeah. Then, sir, if we apply the De Morgan's law, like I'm just getting union
so
of
again
A
by C,
complement.
right? By C,
Yeah, sir.
if I take the complement of this,
Yeah, sir. Then I will get intersection of
let's
A
see.
complement whole complement.
This is nothing but intersection over all I.
Yeah.
AI complement complement, which is AI belongs to
Yeah.
F. Right?
Yes, sir.
Simple, isn't it? How many of you think that it was easy? You can say it, it's okay. I mean, be interactive, okay?
yes, sir.
It was easy, right?
Yes,
You
yes.
might be wondering how people came up with this proof. Of course, this is an easy proof, but still, sometimes what people do is reverse engineering, right? So I'll just write it, but I won't, I'll erase this. See, I want to prove intersection AI belongs to F, right? I know that union AI belongs to F. So somehow I have to convert that into union, right? So how do you convert this into union? One way is complement, right? So the whole complement also belongs to F, right? So I'll probably do it in, okay, this belongs to F. So that means I know that this also belongs to F. Let's try this out. This is nothing but union AI complement belongs to F. Well, this is obviously true, right? Do you agree? See, this implies this, we are done. But this is obviously true. Why? If AI belongs to F, AI complement belongs to F. If AI complements belongs to F, union belongs to F, right? So you are done. So you start here and go back. That's all. Is that fine? Sometimes, reverse engineering works. You just see what is required and see under what condition we can prove that. So just do some sort of a reverse engineering. Okay. Is that fine? So that's why when you, in mathematics, whenever you define something, you will make sure that you will only define that, you will only make statements that are not redundant. So you need these three, but the rest that I'm going to write are redundant. You could have put this countable intersection in the definition, but that's redundant. Okay? Is this fine? Now you might be wondering, I'll leave this as an exercise, or I want you to think about this. For example, omega is 0 to 1. What is this? Maybe I am going to rotate a disk and measure the angle, divide by 2 pi. So 0 to 2 pi will become 0 to 1. Right? That's an experiment. So what is F? Okay. Think about it. Okay. I want you to think about this. Any idea? So maybe I'll pause for a minute. So what will be F here? What will be F? Any idea?
So two of the events are sure for sure, sir. First one is the trivial, and the second one for the 2 to the power this.
Oh, 2 power omega is okay. Yeah, you are right. I mean,
It will get whole R, I think. So.
No, so
Something.
okay, I'll let you think. Okay, so I won't answer this now.
Okay, sir.
Okay. So these are axioms for events, but of course I want to attach probability. It turns out that I can attach probabilities for the sets in F sigma algebra. Okay, so let's look at axioms of probability now. Okay, so what are the axioms of probability? So first of all, you are going to attach. So let me just write it as definition, or if somebody wants to take it as an axiom, it's an axiom. So what is a probability? What will it do? It will take, for example, sets from or points from F. F is the sigma algebra, right? So it will take points meaning sets from F, and attach a number called probability, right? So 0 to 1. So you cannot say a probability of something is 1.3, right? That's not possible. So you have to restrict itself to be 0, 1. Okay, such that the following things need to be satisfied. First of all, probability of the entire set is 1. That is something that is required, right? The second thing would be, for every disjoint A1, A2, etc., countable belonging to F, probability of disjoint union. So basically, you are asking the probability of the union of pieces is equal to sum of the probabilities. Okay, is this clear? These are the axioms. It's very simple. So probability takes points or sets from F and attaches a number called probability, and that number should be between 0 and 1. That means it's non-negative. And probability of omega, the entire set would be 1. You give me any disjoint pieces in F, the probability of the union should be equal to the sum of the probability. Well, just to give you an analogy, so if you look at, for example, some region, for example, this is the region. I cut this region into disjoint pieces like this. This is the region A1, A2, A3, A4. I'm going to look at area of this. So the area of A1 union, A2 union, A3 union, A4 would be equal to the area of this entire thing, right? So area of this would be equal to the sum of the areas of individual, right? That is the analogy, right? So probability, whatever it is analogous to area, perhaps volume, and many other things. Okay, so that's why whenever you study these things, what does area does? It measures the area, right? Volume measures volume and so on. Probability measures chances. Area and volume measures the size, etc. So there is a branch called, or the topic or the area called measure theory, which talks about these things, and probability is one example of that. Okay, is it fine? Okay,
Yes.
let's look at a few consequences. So what can you say about probability of null set?
0.
Why is that? How do you prove that? Huh?
So it's a simple application, sir, of the second property, sir.
Okay, so
Like, sir, we can write the
so
omega union phi.
omega, yeah, so omega, I can write it as omega union phi.
Phi, yes.
So omega and phi are disjoint, obviously. So probability of omega, which is 1 by axiom 1, so A, right? This is nothing but probability of omega union null, which is nothing but probability of omega plus probability of null. But this is 1 by, this is by C, B, I think. This is by A plus probability of null. So this implies probability of null is 0, right? Easy. Do you agree? So what will be the next one? Obviously, probability of A complement. Well, whenever I write A, B, C, these events, I'm inherently assuming that these sets belong to F. What can you say about this probability of A complement? Can somebody tell me what is the answer?
So 1 minus probability of A.
Okay. What is this? How do you prove this?
So again, just
Yeah, see, again,
A
let's
union
look
A
at,
complement is equal to whole
yeah,
space.
so let's look at reverse engineering.
Okay.
Well, this is really sloppy, but I'll write this A complement plus probability of A is 1. The moment you see this, it's the sum of two probabilities is 1. Well, the moment you see this, looks like, well, this is same as probability of A union A complement, right? What is this? This is nothing but probability of omega, right? You have to go in the opposite direction. I know that probability of omega is 1, right? 1 is probability of omega. But probability of omega, I can write it as A union A complement. But A and A complement are disjoint, so I can write it as probability of A complement plus probability of A. Well, by that we get this. Is that fine? So you go in the reverse direction. Okay? Okay, so there are a few other property. Maybe I'll just write it. A1 is contained in A2, is contained in and so on. Okay, so what if I take the intersection of I equal to 1 to infinity? Yeah. What do you think is the answer? Can somebody guess what is the answer?
Probability of A1.
A1.
Huh?
Probability
Probability
of
A1.
A1.
A1. Okay. Why is that? Well, that's the least, right? That's the least that you have, right? Okay, so now let me reverse this. Now what can you say? Huh? See, A2 is sitting
So
inside
1.
A1. Huh?
1.
Well, why do you think it's 1? Okay, can you give me a counter example where it's not 1 based on your intuition? Not now, but maybe in the next class. So this will be limit n tending to infinity probability of an. Okay, it's the last event in this chain of events. Well, we will prove this in the next class.
So
So
isn't it going to be the whole total number
no,
of
not
sets that
necessarily, right? Not necessarily. For example, 0, 1. Okay, I'll take 0 half minus plus 1 by n. Okay, this will be my set. This will be an. A1 will be what? Well, I think did I? Okay, so some 2n. Okay. Okay, so when A1 1, A2 is half plus 1 by 4. A3 is something like that, right? So eventually what happens as this goes to what? 0 half, right? Well, it's not omega which is 0 1, right? Clear or not clear this thing? Hello?
so can I explain once more?
Okay, so
So you can start the set from 0.1 instead of 0.
Huh?
You could start that set from 0.1 instead of 0.
Okay, so let's look at maybe 1 by 4, and
Yeah.
this point is, for example,
Half plus 1 by 3
plus 1 by
plus
2n.
1 by 3 n. Okay.
2n, right? So what will happen? So this will be my an. What is a1? A1 is 1 by 4 to 1. A2 is 1 by 4 to half plus 1 by 4. This is 3 by 4. right? And so on. What will be A infinity, whatever that is? That will be half. Okay, why did I say 1 by, wow, it's 1 by 4, comma, 1 by 2 included, right? Which is not equal to omega. What is omega? 0, 1, right? Okay.
Yes.
Anyway, so we will continue with this in the next class. We will look at a few of these axioms and a few of these consequences and try to prove these consequences. For those, how many of you think that it's been very difficult? Is it difficult?
Sir, can you share the PDF
No, sir.
writing with us?
Yeah,
Notes.
sure. I can share.
Certain points
Because
are
there are some new terminologies, that's why omega and all, we used to know by some other terminology, that's why maybe some confusion in the first class, maybe.
Okay, no problem. No, you'll get used to it. Okay.
Yes, sir,
Get
yes.
used to- I will be consistent throughout. Omega FP, omega FP. So nothing. I'm not going to
Okay.
deviate from that.
Okay, sir. Okay, sir.
And for those who think it's very elementary, I'll get into more complicated things soon. So there will be, I'll teach concentration inequalities, all those things, much more complicated than what we are doing. Okay, so please attend that the other meeting today. So introduction to whatever. I think we would have sent you the email, link, right? Okay.
Yes, sir.
Please attend. We will not take more than half an hour. Half an hour is the max.